Good morning, friends. We are going to discuss about the other numerical of the MCQ question 14 oscillation. Right. Already we discussed the 7 MCQ question. How we solve it. We also discussed the method. First, read the question carefully and also note down what are the information are given and what we have to find out from the given information. And what are the equation we are using or we can apply for the given information, and we have to find out the physical quantity. So that is the important thing. Now on the base of this we are going to discuss the more question. Right? Now there is a frequency of the oscillation of a mass M suspended by a spring is M. If the mass is cut to 1/4, then what will be the frequency of the oscillation? Now what it says that one body of mass M is suspended at the end of a spring. At that time the frequency of the oscillation is that. Now in second part the mass is cut 1/4. 1/4 part of this body is now cut. What is the new frequency? F2, we have to find out. Spring is given same, but only the mass of the suspended body is reduced by the 1/4 of its given mass. So what is the new frequency? Now we know that the frequency of the oscillation of a spring F is equal to 1/2 pi under root of Km. The frequency of oscillation is F is equal to 1/2 pi under root of K upon M. Now listen, spring does not change, therefore the force constant is not changed. Only the suspended mass is changed, therefore F proportional to the 1 upon under root of M. Therefore, the ratio of the new frequency to the given frequency F2 upon F1 is equal to under root of M1 upon M2. Now M2 is 1/4 of already this. Therefore, M1 upon M1 by 4. Only 1/4 mass is remaining. M1 is equal to M. M2 is equal to M by 4. So it remains only the root 4. Therefore F2 upon F is equal to root 4 is equal to 2. Therefore the frequency of the oscillation becomes the double of the initial. Now listen here again, the frequency of the oscillation of a mass M suspended by a spring is given there. Therefore, here we have to apply the equation of the frequency of oscillation. F is equal to 1/2 pi under root of K upon M. Now, mass is cut and remaining mass is 1/4 of initial mass. Therefore, M2 is equal to M by 4. What is the F2? So, from this equation of oscillation of frequency, F is equal to 1/2 pi under root of K upon M. K is constant, spring does not change. Therefore, F is inversely proportional to the square root of M. Therefore, initial F1 proportional to the 1 upon under root of M1 and final frequency F2 proportional to the 1 upon under root of M2. Taking the ratio of these two frequency F2 upon F1, so we obtain is equal to under root of M1 upon M. M1 is the initial mass M and M2 is 1/4 of initial mass. Therefore, M1 by 4. M1 cancel. 4 is in denominator of denominator, comes into the numerator. Therefore, under root of 4 is equal to 2. Therefore, F2. F1 is F. F2 upon F is equal to under root 4 is equal to 2. Therefore, new frequency is 12. That means, if the instead of the body of mass M, we suspended the body of mass M by 4. So its frequency becomes the double of the initial. Only here we have to apply the equation of frequency of oscillation, right? Okay. Now the next numerical, the ratio of the force constant of the two springs is given 1/2. Therefore, K1 upon K2 is equal to 1/2. And the mechanical energy of that is 2/9. E1 upon E2 is equal to 2/9. The ratio of the amplitude of the two bodies suspended at the end of the spring is, we have to find out the ratio of the amplitude of these two bodies that perform the oscillation. So there is the equilibrium position, so it oscillates like this way, there is the amplitude. We know the equation of total energy, E1 upon E2. E1 is equal to half K1 A1 square upon half K2 A2 square. That is cancelled. E1 upon E2, that is given 2/9. K1 upon K2 1/2 into A1 upon A2 whole square. Right? Require the ratio of amplitude. Therefore, A1 upon A2 whole square is equal to 2/9 into 2. That means the 4/9. Taking the square root on both sides, therefore we obtain A1 upon A2 is equal to 2/3. 2/3. So there is our answer. We have to find out the ratio of the amplitude. Again, the ratio of force constant of the two springs is 1:2. Therefore, K1 upon K2 is 1/2. And the mechanical energy of them is 2/9. E1 upon E2 is 2/9. What is the ratio of the amplitude of two bodies suspended at the end of the spring? We have to find out the ratio of the amplitude. Here the ratio of the mechanical energy, that means the total energy, is given. Therefore, we are using the concept of, or the equation of mechanical energy, E is equal to half K square. Here the two energy are given. Therefore, E1 upon E2 is equal to half K1 A1 square upon half K2 A2 square. Half cancel. K1 upon K2 already given 1/2, and A1 upon A2 whole square we have to find out. E1 upon E2 given the 2/9. Therefore, 2/9 is equal to 1/2 into bracket A1 upon A2 whole square. Therefore, A1 upon A2 whole square is equal to 2/9, and multiply these two, therefore 4/9. Taking the square, we obtain A1 upon A2 is equal to 2/3. That is the ratio of the amplitude of the given two spring having the force constant ratio is 1/2, and also the ratio of the mechanical energy is 2/9. Right? After that, if the length of, next question, that is depends on the second pendulum. What is the second pendulum? The pendulum which has the periodic time is 2 seconds is known as the second pendulum. Therefore, periodic time of second pendulum T is equal to 2 seconds. If the length of a second pendulum becomes the 1/3, so what will be its periodic time? Initial length L1 is equal to L. At that time, the periodic time T1 is equal to T is equal to 2 seconds. Now L2 is equal to what? The 1/3 of initial. 1/3 of initial. That means the L/3. We have to find out the periodic time. So we know that the periodic time T is equal to 2 pi under root of L upon G. 2 pi L upon G. Here the change take place as the length changes. Therefore change take place in periodic time. Therefore periodic time is directly proportional to the square root of length. Square root of length. Right? Therefore we can write T1 proportional to the under root of L1 and T2 proportional to the under root of L2. Directly we can write T2 upon T1 is equal to L2 upon L1. L2 upon L1. Now L2 is L by 3. That is the L by 3. And that is the square root. Therefore square root of L by 3 and L1 is also L. So LL cancel 1 upon root 3. 1 upon root 3. Therefore T2 is equal to T1 into 1 upon root 3. T1 is the periodic time of a second pendulum, that is the 2 seconds, upon root 3. That is the new periodic time of a second pendulum if the length of a pendulum is decreased by 1/3. Again, the periodic time of second pendulum T is equal to 2 seconds. Now, if the length of second pendulum becomes the 1/3 of initial, what will be its periodic time? So initial length is L, T1 is equal to T is equal to 2 seconds for second pendulum, and final length of a pendulum is L by 3. So what is the T2? So we know the equation of the periodic time of second pendulum or the pendulum. T is equal to 2 pi under root of L upon G. Here only the length changes, therefore periodic time is directly proportional to the square root of length of a pendulum. Therefore T proportional to the under root of L. For initial length, so we can write like this way: T1 proportional to the under root of L1 and T2 proportional to the under root of L2. Taking the ratio of these two, T2 upon T1 is equal to under root of L2 upon L1. L2 is L. L2 is L by 3. This is the L2. And L1 is L. LL cancel. Therefore 1 upon root 3. Therefore T2 is equal to T1 into 1 upon root 3. But T1 is equal to 2 seconds. Therefore 2 upon root 3. So that is the new periodic time of a simple pendulum if its length is 1/3. Now, next is particle executes the simple harmonic motion have the periodic time 0.05 seconds. T is equal to 0.05 seconds. And amplitude is given the 4 centimeter. Then, what is its maximum velocity? We have to find out the V maximum. Now we know that the equation of the maximum velocity, V maximum is equal to plus or minus A omega. Because whatever the particle performs the simple harmonic motion, at the mean position its velocity is maximum. And this maximum velocity is equal to A in omega. But here omega not given, periodic time is given. We know that omega is equal to 2 pi upon T. Therefore, A into 2 pi upon T. Because omega is equal to 2 pi F and F is equal to 1 upon T. Therefore, 2 pi upon T. Now, all values are given. Amplitude is given 4 centimeter, convert into meter. 4 into 10 is 2 minus 2. Omega 2 pi 3.14, or keeping this way pi, upon periodic time is given the 0.05 second. Therefore, there is the 1.6 pi meter per second. That is the maximum velocity. Again, the particle performing the simple harmonic motion having the periodic time T given 0.05 second and amplitude is given the 4 centimeter. Then what is the maximum velocity? We know the equation of the maximum velocity A omega. but omega not given. We know that the omega is equal to 2 pi f or the 2 pi upon t. Therefore, A into 2 pi upon t. Substitute the value. Amplitude is given in centimeter, convert into meter. 4 into 10 is to minus 2. 2 pi, 2 into pi as it is upon periodic time t, 0.05. Therefore, 1.65 meter per second. Clear this? Okay. After that, the next. To spring of the first constant k into k. Here the k1 is equal to k, and second spring, first constant k2 is equal to k. That are connected to a mass m as shown in the figure. Here there is the mass m is placed on a horizontal surface. It can move frictionless on this surface. Here the two springs are connected like to this. Right? It's shown in the figure. The frequency of oscillation is, what is the frequency of oscillation? Now the histering force in spring 1 is K1Y and spring 2 is K2Y. Because AC displaces the body by Y distance. So the histering force produced in both springs. Therefore, the histering force F1 is equal to K1Y and F2 is equal to K2Y. K2 and total force F is equal to F1 plus F2. F is equal to Ky is equal to here. Y is common, K1 plus K2Y. Y cancel. Therefore, the equivalent force constant K is equal to K1 plus K2. There is the equivalent force constant in this condition. Now the frequency of oscillation F is equal to 1 upon 2 pi under root of K upon A. K upon A. Substitute the value of K. Therefore, frequency of oscillation is 1 upon 2 pi under root of K1 plus K2 upon A. K1 plus K2 upon A. But here, what is given? K1 is equal to K and K2 is equal to 2K. Substitute it here. Therefore, 1 upon 2 pi under root of K plus 2K, 3K upon A. 3K upon N. That is the frequency of oscillation. Again, two springs of the first constant K and 2K are connected to a body of mass n as shown in the figure. The frequency of the oscillation of a body. So as we displace the body by the y distance, so what's happened? The stirring force produced in both spring K1 and here another spring 2. And this stirring force F1 is equal to K1Y and second spring stirring force F2 is equal to K2Y. And total stirring force F is equal to F1 plus F2. So total stirring force Fky is equal to here K1Y plus K2Y, Y common, that is cancelled. Therefore, the equivalent force constant of this combination is K is equal to K1 plus K2. So when the body performs the simple harmonic motion, the frequency of its oscillation F is equal to 1 upon 2 pi under root of K upon A. But K is equal to K1 plus K2, therefore F is equal to 1 upon 2 pi under root of K1 plus K2 upon A. K1 is equal to K and K2 is equal to 2K. Therefore 3K upon M. F is equal to 1 upon 2 pi under root of 3K upon M is the frequency of oscillation. Clear it? Okay. After that, the spring of first constant K is cut into two parts such that the length of one part is double to another part. Right? So here the total length is L one part is L1 and second is L1 is 2L2. Therefore, total length L is equal to L1 plus L2. But L1 is equal to 2L2. 2L2 plus L2. Therefore, 3L2. L is equal to. And L is equal to L1 plus L2. L1 plus L2. Therefore, L2 is equal to L1 by 2. L1 plus L1 by 2. Because the length of the first part is double than the second part. Therefore, the second part has the length is the half of the first part. Right? Therefore, L is equal to 3L1 by 2. 3L1 by 2. Okay. Now, the historic force K1L1 is equal to K2L2 is equal to KL. Here we are comparing K1L1 is equal to KL. Therefore, K1L1 is equal to K. L is equal to 3L1 by 2. L1 cancel. Therefore, K is equal to, the K1 is equal to 3 by 2K. 3 by 2. There is the force constant of a larger part. Again, a strain of the force constant K is cut into the two parts, such that the length of one part is double to the another part. Length of the first part is double than the second part. What will be the force constant of large part? Now, total length L is equal to L1 plus L2, but L1 is 2L1 L2. Therefore, 2L2 plus L2. Therefore, L is equal to 3L2. Now, in terms of L is equal to L1 plus L2, L1 is as it is. Now, the second part has the half length of initial or of first part. Therefore, L1 is equal to L1 by 2. Therefore, 3L1 by 2. Now, K1L1 is equal to K2L2 is equal to KL. We have to find out the force constant of large part. Large part is our L1. Therefore, K1L1 is equal to KL. Therefore, K1L1 is equal to KL. Now we have to substitute the value of L in terms of the large part. L is equal to 3L1 by 2. Therefore, K1 is equal to K1L1 is equal to K 3L1 by 2. L1 cancel. Therefore, K1 is equal to 3 by 2 K. There is a force constant of large part and force constant of small part. If there is asked, so a small part is that we compare the K2L2 is equal to KL. Here we substitute the value of L in terms of the small part. Therefore, K2L2 is equal to K into 3L2. That is cancel L2. Therefore, K2 is equal to 3K. That is the force constant of the small part. That is the force constant of large part. So in this part we discuss generally the most of the MCQ question on the base of oscillation, periodic time, and also for simple or a simple pendulum, right?